The types of equilibrium calculations that you have been doing apply not only to KSP, solubility problems, and to acid-base problems. They can apply to any type of equilibrium situation. He gives you an example 8.8. He gives you an example of another type of equilibrium problem that you can work. This particular problem, there was really nothing too complicated in it. I'm not going to work that problem out. I am going to do another type of problem on the board that has a couple of things that you need to watch out more carefully for that you will see in some of your homework problems. So we're going to work through this problem instead so you'll be able to see what this looks like. Okay, so the problem is this. A 1 liter container filled with 1/2 mole of hydrogen iodide at 448 degrees Celsius. The value of K is 50.5 for this reaction. We want to know what the equilibrium concentrations are. Now, the particular problem that I chose does have does have the amounts of the gas in moles. Sometimes you will see instead of concentrations or moles of the gas, sometimes you will see it done as pressure, and pressure can be treated exactly the same as molarity or exactly the same as moles, just because of the way gases behave. Again, that's something that we learned back in first year chemistry. So if you see pressure, if you see atmospheres, if you see torr, well, no matter what units you see, you can plug those into an equilibrium expression just the same way that you can molarity or number of moles for a gas. All right, so let's look at this particular problem. This one says that I'm starting out with 1/2 mole of hydrogen iodide. So initially here, I don't have any hydrogen gas or any iodine gas. So because this is an equilibrium, it's going to be able to go both ways. And so this is going to lose X amount. But some of these problems don't always have all ones for coefficients like most of the problems we've been working. So make sure that you're careful when you work these kinds of problems. You can always do a stoichiometric calculation if you're not sure how that's going to look. So for example, if I start out with 1/2 mole of HI, how many moles of iodine am I going to come up with? So for every 2 moles of HI, I'm going to have 1 mole of H2. And so if I take 1/2 and I divide it by 2, that's going to be 0.25 moles of H2. So I'm going to have 1/4 of what I started out with, okay? So that means you're going to have to watch here because this ratio is 1 to 2. That means that the amount that this loses, I can't just transfer an X over here, okay? So therefore, what that means is that this is going to be 1/2 of X, and this is going to be 1/2 of the value of X that it gains, okay? So you can use this equation right here to figure out what this X is going to be as far as to how much it's going to gain or how much it's going to lose. All right, now knowing this, this is how much we're going to have at equilibrium, because again, if you think about if I start out with 2 moles of this, I'm going to end up with 1 mole of this. If I start out with 1/2 mole, it's going to end up with 1/4 mole. So I'm going to end up with half the amount that I did of whatever I lose over here. So if I lose X, I'm going to end up with 1/2 of X for each one of these, okay? So watch those coefficients carefully. All right, now I can use the equilibrium expression. So my equilibrium expression is going to be HI, the quantity squared, over H2 times the concentration of I2. Now, it tells me that the equilibrium constant is 50.5 and HI is 0.50 minus X, and that has to be squared. And then on the bottom, I have 1/2 X times 1/2 X. Okay, I'm going to show you a little trick here because this is going to be very messy. I could solve it using the quadratic formula. That's not a very fun way to do it. And with the way this particular problem is set up, there's a neat little trick that we can actually employ here. So that trick is this. If you notice, the top is squared and the bottom is squared because 1/2 X times 1/2 X is the same as 1/2 X, the quantity squared, right? So what if I just took the square root of both sides? What if I did that? If I took the square root of both sides, then I would have 0.50 minus X, and I would have 1/2 X on the bottom. And then if I take the square root of 50.5, I'm gonna have 7.11. Now, this problem is easy to solve. I only have X's, I don't have anything in powers, and I can solve that equation very, very easily, and X comes out to be 0.11, okay? Now, this won't work all of the time, but do keep an eye out for something like this because sometimes you can simplify this and you don't have to worry about using the quadratic formula then. All right, so therefore, if X is 0.11, what is that going to make my equilibrium concentrations? Well, my HI concentration, hydrogen iodide, is going to be 0.50 minus 0.11, which is going to give me 0.39 molar. And my hydrogen concentration is going to be the same as my iodide concentration, which is going to be 1/2 of 0.11, which is going to be 0.055 molar. Okay? So there is that type of problem. Again, the things you want to watch for here, if these coefficients are not all ones, you're going to have to be very, very careful of that and make sure you have the right numbers on X's, and then obviously the other neat little trick that you can employ. It doesn't work super often, but when it does, it's really nice and you don't have to use the quadratic formula that way. All right.